In this video, we're going to start to introduce the topic of infinite series. Now remember, a series itself is a sum of a number of terms generated by some explicit formula for a sequence, which here is indicated by AI. AI would generate the terms A1 plus A2 plus A3 and so forth, and series means we're adding them together. An infinite series means that we're going to try to add an infinite number of terms together. Now here's the thing, is we can't actually add an infinite number of terms. It's not actually a true, infinite series are not true sums because we don't know exactly how many terms to add together. But what we can do is we can look and see what the individual sums are doing. So as I start adding more terms together, from 2 terms to adding 3 terms to adding 4 terms together, to see if the sums are narrowing in on our value. And if the sums are narrowing in on a value, then we can predict what the infinite sum would be. Well, if the sums are starting to narrow in on a certain value, we will say that the series will converge. And if a series converges, then we can use it to find the actual sum. So looking here at this first couple of examples, we want to find the first 5 partial sums of the series that are given as follows. Well, the first partial sum is going to be equal to the sum of just the first term, which the first partial sum would just be equal to whatever the first term is, 0.2. The second partial sum is going to equal the sum of the first 2 terms, which would be A1 plus A2. So if I add the first 2 terms together, we're going to wind up getting 0.22. The third partial sum is going to be the sum of the first 3 terms, so A1 plus A2 plus A3, which is going to be, if I add the first 3 terms together, it would be 0.222. And you see where this is going. The fourth partial sum would add the first 4 numbers together, and we wind up getting 0.2222. And then my fifth partial sum, if I had the 5th number, would just simply put another 2 on the end there. And so the question is the sum converging? Well, the way I tell if the sum converges is I'm looking at these numbers for my sums: 0.2, 0.222, 0.32s, 0.42s, 0.52s. As I continue to add more terms together, my sum is approaching a value of 0.2 repeating, or 2/9. So since it was narrowing in on a value, then I could say yes, it does converge. All right, looking at the second problem here, so I'm given the terms 2 plus 8 plus 14 plus 20 and so forth. And I want to list out the first 5 partial sums. Well, my first partial sum is simply going to be 2. The second partial sum is the sum of the first 2 numbers, so 2 plus 8, which is going to give me 10. The third partial sum is the sum of the first 3 numbers, which would be 2 plus 8 plus 14, which would give me 24. The fourth partial sum would be the sum of the first 4 numbers, 2 plus 8 plus 14 plus 20, which gives me 44. And then the fifth partial sum would be the sum of the first 5 numbers. Well, if I continue that pattern on, and the next number, which isn't listed, is 26, because I'm adding 6 each time. And so that fifth partial sum, instead of continuing to add numbers over and over and over again, the fifth partial sum would be equal to the fourth partial sum plus the next number I wanted to add, which in this case would be 26. And 26 plus 44 is going to give me 70. So if I want to know if the series converges, I'm looking at the sequence of sums here. So I'm looking at the numbers, basically 2, 10, 24, 44, and 70, and so on. I'm wondering that as I continue to go this way, are there values approaching a number? Well, as I continue to go to the right and add more numbers together, we keep getting larger and larger and larger, and we're not narrowing in on a value, so it's heading towards infinity, and we will say this does not converge, which means it diverges, because it's not narrowing in on a certain value. All right, let's look at one more. So I want to find the first 5 partial sums. So the first partial sum is just going to equal the first term, which is 3. The second partial sum is going to equal the sum of the first 2 numbers. So 3 minus 3 gives me 0. All right, well, that one got smaller. Now I go find a third partial sum, which would be equal to my second partial sum plus the next term, which is 3, so we get 3 again. My fourth partial sum, add the first 4 numbers together, we're going to get my third partial sum plus the next term, which is -3. We get 0. And my fifth partial sum, if I continue the pattern of terms, the next number we would have be +3. And so we would have 0 plus 3, and that sum would be equal to 3. So I'm looking at the pattern of the sequence of sums. 3, 0, 3, 0, 3. And I'm wondering that if I continued this on forever, would I be approaching a certain value? Well, all that's happening is you're alternating between 3 and 0. You're not narrowing in on a certain value. So this will not converge, it diverges. So if you don't converge, you diverge. Now, this process of determining the convergence of a series, an infinite series, is an important study in calculus. Now, what we can do is, if the sequence of partial sums, that was the parts of what we highlighted. So the numbers for the partial sums, we were looking at that sequence, not the sequence of numbers I added, but the sequence of their sums. If the sequence of sums converges in on a number, then we can say that the overall series is convergent. Now that brings us to the question, well, is there a way, how would I figure out if a series will converge or not without having to write out all the sums? And there's a number of tests, but one of the first tests that we're going to look at is called the Nth Term Test, or the limit test. This test is strictly to tell you if a series will diverge or not. So this limit test, or the Nth Term Test, says that if the limit as n approaches infinity of a of n is not equal to 0, so this is your explicit formula inside of the series, then the series of a of n will diverge. Notice how it does not say anything about converge. Strictly tells you that a series will diverge if the sequence of terms do not go to 0. This is the Nth Term Test. The converse of this is not always true. That is very important. So this only tells you if you will diverge. So only tells you if it diverges. Tells if diverges. So if that limit does equal 0, then we really don't know. We would have to do some further investigation. To figure out, so I want to do the Nth Term Test. So the Nth Term Test, or the limit test, is basically saying take what is inside of the series here and evaluate the limit as n approaches infinity of 2n plus 1. Well, as I start increasing the size of n, 2 times n plus 1 is going to continue to get larger and larger and larger, which means it's going to be approaching infinity. So I'm going to say equals infinity here. And so what that means is we failed the limit test. So since our limit did not equal 0, so the limit as n approaches infinity for 2n plus 1 did not equal 0. We said it equaled infinity. That means our series diverges. All right, so let's look and see what is happening here. So if I'm looking at the graph of 2n plus 1, and I'm just labeling it, I'm looking at what is happening as I work my way farther and farther to the right. Well, as I continue to go farther and farther to the right, you'll notice how my values continue to get larger. Now, this isn't the series. This is the sequence itself. That's an. See how it's not approaching 0. Therefore, that's the reason why it failed the limit test, and we said it diverges. Now, if I graph the series, the sum of my partial sums, that'll be here in red. What you'll notice is that since my sequence did not approach 0, let me zoom in. You'll notice that the series itself is not converging because they just continue to get larger and larger and larger. You look at those red dots. So if it actually converged, our red dots would be approaching a certain number that we could predict its value. In this case, it is not. All right, looking here at this next function. So I want to know, will this converge or not? We're using the Nth Term Test, or the limit test. So the Nth Term Test. What you're going to do, if I want to know if that series converges, is I'm going to take the equation inside of it, and I want to know, I'm asking myself, what is happening as I increase the size of n without bound? So 1/2 to the n minus 1 power. What is happening to that 1/2 as I increase the size of n? Well, if I keep applying and making bigger and bigger and bigger exponents for 1/2, the actual value, you think about, I have 1/2 to the 0 is 1, 1/2 to the 1 is a half, 1/2 to the second is a quarter. As the exponent gets bigger, I get smaller values. In fact, you're going to get smaller and smaller and smaller. You're going to approach a value of 0. So the result of our limit test is that we know really nothing. We don't know if it converges or diverges. So we need to go look at this graphically. So look at graph. All right, so here in purple, we're looking at the actual graph of the sequence itself, the explicit formula, which is 1/2 raised to the n minus 1 power. And we look and we see that as you go to the right, that graph of terms, the sequence of terms are getting very close to the x-axis, that they approach 0. Just because they approach 0 does not mean the series converges. All right, there's a difference between sequence and series. The series itself, I'm getting ready to graph here in red. I'm going to highlight that. So it plots the sequence of partial sums. And so if I look, the first couple of dots are off my screen. So I need to change my scale here and zoom out. And what you'll notice is, looking at this, notice how my sequence of partial sums, they level out here in terms of what they're approaching. And they're approaching a value of 2. So graphically, since our sequence of partial sums converges in, narrows in on a certain value, y value, in this case of 2, we can say that the series converges. So looked at the graph and we said, yes, it converges to a value of 2. All right, let's look at this next one. So I'm given the infinite series from n is equal to 1 to infinity of 1 over n. This is actually called a harmonic series. It's a lot of time is spent focusing on this in calculus. But when I go through and I'm looking at this, so if I want to know if this series converges or not, we're going to do the nth term test here. So the nth term test says that, well, I can't tell you if you converge, but I can guarantee you diverge if this limit here of what is on the inside my explicit formula, if it does not equal 0, then it will diverge. Well, the value of 1 over n, as n continues to increase forever, so if I divide 1 by an increasingly large number, this is approaching 0. So I cannot assume that this converges or diverges. So the limit test doesn't really tell me anything. So in order to determine if it converges or diverges, we need to see a graph here. So we'll start here. We'll look at the graph of the sequence itself, a of n, and that's here in purple. And you notice how we start at 1, and as we work our way to the right, it gets closer and closer and closer to that x-axis. So that limit, it was approaching a value of 0. Now, we're not trying to determine the convergence of a sequence. We're trying to determine the convergence of a series. So I'm going to plot now the sequence of partial sums. Now we look here, and it starts plotting it in red, and it's like, okay, it's starting to go off my graph. Let me zoom out and see if it's narrowing in. So I zoom out, and I look, and it's like, well, it continues to get larger and larger and larger. It's not flattening out. It's starting to flatten a little bit, but it's continuing to get bigger and bigger and bigger, even as I start to increase the number of terms. So let me increase the number of terms even farther. So I'm at all the way up to 850, and I zoom out. Notice how this thing continues to get bigger. Since it's continuing to get larger, it is not converging. This is actually a diverging sequence or series here. So it does not converge, therefore it diverges. And if it diverges, we say no sum. All right, looking here at this next problem. So I want to know if the series converges here when I'm going from 1 to infinity of 1 over n squared. Here's the important part about determining if a series converges or not. Is if I know if a series converges, I can approximate its true sum. And so sometimes we don't have formulas to get sums, so we have to approximate them. And a lot of time is spent in terms of finding these sums in higher level mathematics. One of the ways we can determine this is by doing the nth term test. And what I can do is say, all right, the nth term test basically is a test for divergence. which means that if the limit as n approaches infinity does not equal 0, I know immediately that it diverges and it won't have a sum. Well, the limit as n approaches infinity, 1 over n squared. So if I divide 1 by an increasingly large number, that is going to be approaching 0, which means that I do not know if it converges or diverges. So the way that we're going to tell at this point is we're going to go see it graphically. So we're going to graph this series and see what it does. And so we're graphing the sequence, or the explicit form, 1 over n squared. And we look here in purple, and you'll see that as you start to increase the size of n, you're getting closer and closer and closer to 0, which we saw that already with our nth term test limit, that it approaches 0. That does not mean I converge. It means I need to further investigate. So let's look at a graph that plots the sequence of partial sums without us writing it out. So I'm going to turn that on here in red. I need to zoom out a little bit so we can see it. And so as I start to add more and more of these partial sums together, my x-axis here represents the number of terms I'm adding together. In this particular case, you'll notice that we are actually narrowing in on a value where if I zoom out, so this top line represents what it is we're approaching, and I look and it's like, all right, we're getting closer and closer and closer. I mean, we're all the way up here if I zoom far enough out, where after adding 700 terms, I'm at 1.643, which is kind of close to the same sum after adding 500 terms. So what I can do is I could approximate this sum. Now, this isn't the exact sum. We're approximating. We're going to round it. And so after adding 839 terms, we're approximately, for our sum, 1.644. Notice how these values converge, narrowed in on a certain sum, this y value. So it converges, and it converges to a sum of 1.644. So converges, the sum does, to a value of 1.644. So the nth term test is a divergence test, and then if it does not, if the nth term test fails, I mean, it doesn't tell me whether or not I diverge or not, then I'm going to graphically go graph my sequence of partial sums and determine if it converges that way.